Well, good afternoon, everybody. Thank you so much for being here this afternoon. The speaker of today is AJS. Suspense. Okay. The speaker of today's AJS is Davide, and the title of his talk is Another Look at Elliptic Homogenization.
È chiuso l'audio?
Okay. So thank you, Maria Teresa, for the wonderful introduction, and thank you everybody for coming here today. So today I'm going to talk about a work that I've done jointly together with Professor Andrea Braides, who's here today, and Giuseppe Brusca, who's here today as well. The name of the work is Another Look, the elliptic homogenization. And so to start in a good fashion, let's start talking. Okay, let's start talking first about giving some remarks about the known and classical results dealing with the elliptic homogenization. So first of all, let's clarify what we mean by homogenization. For us, homogenization will be the mean. Will mean studying the asymptotic analysis of solutions to minimum problems related to oscillating function of this fashion. So where we have a fixed function f, and the dependence on epsilon here is given by this small parameter epsilon in the spatial variable of this function f, and this function will depend on functions, will be valued in functions u which are in Sobolev spaces W1P. And for us, homogenizing will mean finding an integral functional f(om), such that for any given forcing term h and for any reasonable boundary condition phi on the solutions u, then as we let this small parameter epsilon tend to 0, the minimum values of these problems will converge to the minimum value of this, let's say, limit problem. And in addition, we require that under reasonable assumptions, this sequence of solutions to this minimum problem will converge to a solution u, which is a solution of this limiting problem. So to sort of formalize better this given of these two different convergences, in 1975, the George and Franzoni introduced a very well-known notion of convergence, that is gamma convergence. Which, I mean, we'll give briefly a definition for those of you who have never seen it. At least on a metric space X, gamma converging will mean that will be the datum of two different inequalities. So first, we have the gamma limit inequality, which will say that for every sequence x epsilon converging as epsilon goes to 0 to a given point x, then this inequality from the right will hold true. And the gamma limit inequality will require us to build a specific x epsilon converging to any given x, for which this inequality from the left instead holds true. And under certain hypotheses on the functional sequence of functional f epsilon, then this notion will imply 1 and 2. In this case, for example, if f is coercive. Let's specialize to what is known for gamma convergence results for the given functionals f epsilon that we defined before. And in the case where f is a function depending on one spatial variable in Rd and one velocity variable always in Rd, and the function f is positive valued, Borel function, then if f is one periodic in the first variable, which we mean periodic on the unit cube with the period of the unit cube, it satisfies these p growth conditions from above and from below, and furthermore we require that in the gradient variable it is convex for any fixed x. Then there is this well-known result, which was proved first by Marcellini in 1978. It was later generalized to vectorial setting, to non-convex energies. One of those who worked in this area was Professor Braides. There are also some results by Stefan Müller. A lot of people have worked on this. Then, the first known results in this subject was proved in 1978 by Marcellini, and says that basically if f is as above, and f epsilon are the oscillating function that we defined before, then they will converge in the strong topology of LP to an integral functional with a function f om now that doesn't depend on the spatial variable anymore, but only depends on the gradients. And there is sort of an explicit formula for this f om, which is given by this cell problem formula. So if you want to know the value of f om at any given vector psi, you have to solve this auxiliary minimum problem. Where I mean the dependence of psi is given here in this here, and here we are perturbing by functions u, which are periodic of period 1 and are in the Sobolev space W1. Well, this formula then specializes in the case where one chooses as P2 and one chooses as f this particular function, which is given by a coefficient A, which is one periodic, is also strictly positive and bounded from above by a constant beta. Then in this case, f om is going to be for let's say abstract reason a quadratic form. And the matrix defining this quadratic form is going to be symmetric, it's going to be elliptic. And in addition, I mean, the formula that we had before specializes to this one right here. Good. This was the first result that sort of inspired our work. The second result is now very well, I mean, it's a well-studied result by Bourgain, Brezis and Mironescu, which was done in 2001. And I mean, in this paper, what they tried to do was give an equivalent definition of Sobolev spaces without ever talking about distributional derivatives. So they wanted to give a definition of Sobolev space, W1P, let's say, only by looking at difference quotients in this case. So what they studied was these so-called Gagliardo seminorms, which are defined for a number s between 0 and 1, and for a scalar valued function. And basically for a given scalar valued function u, it is given by this double integral. Here we have the dependence on S and on P. And the idea is that, yeah, at least when you value this difference quotient near the diagonal, you should recover the, under reasonable assumption u, you should recover the gradient. So these seminorms are used to define fractional Sobolev spaces, so the spaces of functions in LP for which this object is finite. But in these spaces, you don't necessarily have distributional derivatives as functions. So the idea of Bourgain and Brezis and Mironescu was, okay, let's look at these objects, and let S tend to 1 from the left. Could it be possible that, for instance, we have this sort of inequality modulo a constant? Well, unfortunately, it is easy to see that this cannot hold true. And unless u is a constant function, this limit is always equal to plus infinity. And also, there is one paper of Brezis on the subject, which is called something like when is a function constant. And one way to look at this is look at this object, evaluate for s equal to 1. If it is finite, then the function, at least if omega is a connected set, is going to be constant. But well, so this limit that doesn't make is always equal to plus infinity unless u is constant. So they had to slightly modify the statement. And what they proved was this remarkable result. If you look at u, a function in LP, with p strictly larger than 1 in this case, because otherwise you have to change slightly the setting. There was this result proved by Davide in 2002, where the setting is BV, not W1P anymore. So we restrict our attention to the case p strictly larger than 1. Then in this case, there is going to exist a constant, which just depends on a dimension and on p, for which if you now look at the limit for s that goes to 1 of this seminorm normalized by this coefficient 1 minus s, then you're going to obtain at the limit the gradient of u in LP to the p times this constant. With the convention, of course, that if u was not a function in W1P in the first place, this quantity is plus infinity. So basically, it's telling you if you want to know a function is in W1P, you don't no need to look at the distributional derivatives. You just need to look at this limit, which doesn't involve any distributional derivative. And if it converges to a number, then simply, if you want to know the pth power of the LP norm of gradient of U, look at this number and divide it by this dimensional constant K. Good. Then later, this result in 2004 was expanded in the sense that it was reformulated in the framework of gamma convergence. So Ponce proved that this object here doesn't only converge pointwise to this quantity here, but it also gamma converges in the strong LP convergence in W1P. And if one wants, this result here is the gamma lim sup inequality for this result, because it tells you that as a recovery sequence, you can choose the constant function U. Good. So what we tried to do was sort of mix these two results together. So we decided to study functionals of the form f epsilon s, where now we have a Gagliardo seminorm, sort of, but inside we have also these oscillating coefficients, the coefficient a with a dependence on epsilon given by this always divided by epsilon. And we specialized to the case where p is equal to 2 for, for the simplicity of computations. So first, what one can do is, okay, let's look separately at what happens if we let first one variable goes to 0 and the other one goes to going to 1. And in this case, for example, if one lets epsilon go to 0 first, one can notice that y is, if one fixes y, this is basically a function in L1. This is an oscillating coefficient at infinity. By the Riemann-Lebesgue theorem, this is going to converge to the average of A on the periodicity cell, that is the unit cube, times the Gagliardo seminorm of U. And then applying the Bourgain Brezis Mironescu formula, one recovers this convergence here. And in the case k equal to 2, actually, the expression of k is, in the case p equal to 2, the expression of k is actually very easy. It is simply the Hausdorff dimension, Hausdorff measure, d-1 dimensional measure of the unit sphere, divided by 2 times the dimension of the ambient space omega. One can do the opposite, and in that case, by the Bourgain-Brezis Mironescu formula, by letting s tend to 1 first, the difference quotients should transform into the modulus of the gradient square, and then by using the homogenization theorem, since now we have a full gradient here, one should recover that the convergence to k times the homogenized functional. So, this is what happens if you let the two convergences happen separately. But if one would like, what we wanted to know, if one could find a scale at which we could do these operations simultaneously. And for example, what we investigated was what is the scale at which 2 happens. So to see what the scale should be, we looked at let's say a hint given by the classical homogenization theorem. In the proof of the classical homogenization theorem, the gamma lim sup is proved by density, and one of the first steps that one has to do is look at affine functions. So functions which are given by xi, scalar x. In this case, a recovery sequence is given by a perturbation of the functions u by means of a periodic function phi, which is oscillating faster and faster, but with amplitude which is going to 0. And in this case, phi is chosen not as any random, clearly periodic function, but as one function, let's say, for which this quantity is minimized. And since this quantity was the auxiliary problem, which was giving the value of A valued at the vector xi, we have this equality. And by density reasons, we may also suppose that the function phi is smooth, so that we can do all our computations nicely. In this case, if u is affine, we plug u epsilon inside of the function f epsilon s, and this is the expression that we recover. Now we have that phi is smooth, so we may develop in Taylor, we may Taylor expand this term around x. So phi of x epsilon cancels with phi of x epsilon, and then we have just a gradient term plus higher order terms. So here we gather the higher order terms, and here we gather the gradient in the scalar product with together with psi. Then one may use a lemma that we're going to state better otherwise later on, which basically tells us that it is not, we don't have to consider all possible interactions in omega times omega, but we can restrict our attention just on, let's say, close interactions. So points where the distance between x and y is at most 1. We'll see that we can do actually better. And then we can, I mean, change coordinate, no? We can change coordinate and variables and set z equal to x minus y. And then this standard inequality to split into different terms. And we see that we have now two terms with a very different behavior. Here we have something which, I mean, this integral here, it is a simple computation, can be shown to be always convergent. I mean, here we have a, which is a coefficient which is bounded from above by a constant, and this object is always convergent uniformly in epsilon. So this object turns out to be a big O of 1 minus s divided by epsilon squared. And so since we wanted to work only with this term, we set 1 minus s much smaller than epsilon squared. So this is the framework in which we have worked. In this case, this object, when you let epsilon tend to 0 and that therefore 1 minus s tend to 0 as well, this object is going to disappear in the limit. So we are left with having to analyze this term. And since here we have first an integration in the z, we may take outside the coefficient a x divided by epsilon and only analyze the integral of this object here. Now, the integral over the unit sphere, we may split it using the Quaria formula as an integral on the radii and then an integral on the spherical shells. By symmetry, this is seen to be equal to this integral right here. And then here we have now a function which doesn't depend on me anymore. We can take it outside. We have a nice integral, which is an integral of a polynomial in rho. We can take care of that very easily. And what we get is this expression right here. So here is the constant k I was mentioning before. Sigma d minus 1 for us is going to be the hd minus 1 measure of the unit sphere. And then we see that we have a term that we like very much, because now we have 1 divided by 1 minus s, which was exactly the term that we had in front of the integration of the integrals. So by plugging this equality back together, what we recover is this inequality right here. But now we recall that both a and phi are one periodic functions. So this integration over the ball omega can just be reduced as an integration over the periodicity cell, let's say, by paying the price of multiplying by the right volume term. And then by changing coordinates one final time and by setting x divided by epsilon equal to y, we recover this expression, which is exactly what we wanted, because now we recall how we chose phi. Phi was chosen in such a way that this, let's say, equality holds true. And since u was an affine function, the gradient of u is exactly psi. And so the term volume of omega times a om psi scalar psi is exactly the integral of a om gradient of u times gradient of u. So we recover exactly, let's say, a constant times the classical homogenization theorem. So we have at least a gamma sup inequality for affine functions. And then this is exactly what we proved. We proved the following theorem under the conditions that omega is a bounded Lipschitz domain of Rn. If 1 minus s seen as a function, as a function of epsilon is such that the limit as epsilon goes to infinity of this quantity is equal to 0, then the gamma limit in the strong L2 convergence is going to be given by the classical homogenized functional times a constant. So let's give an hint of the proof. So the gamma Lipschitz inequality is almost proved. What we have to do is just do it now for piecewise affine functions, and then reason by density to prove it for any function in W12. I mean, this is sufficient because we know that affine functions, piecewise affine functions, are dense in the strong W12 topology with in W12. And then this will allow us with this simple line of proof to show that the gamma limb soup inequality holds for any u, knowing that it holds for piecewise affine functions. So we have to concentrate only on piecewise affine functions. So we suppose, for instance, that u is given by a function which is affine on any given simplex of a triangulation of omega. And the idea will be to redo exactly the procedure that we did before to construct a recovery sequence. So on any simplex, we will perturb our psi I times x plus this constant with a periodic functions given by the minimization of the auxiliary problem. The only thing that we have to be careful is that we need to then glue together back the pieces in such a way that it is continuous. Because I mean, a piecewise affine function in W12 has to be continuous in order to be W12. So what we do on any given simplex, we consider some smaller simplices, delta I to epsilon, which is a simplex with distance to epsilon from the boundary of delta I, then an intermediate simplex, and then one considers cutoff functions which are smooth between the inner triangle and this intermediate triangle. And then, as I mentioned before, phi I are going to be auxiliary functions minimizing this auxiliary problem. And then the recovery sequence is given exactly by in the procedure I've just mentioned. So we perturb by this term phi I, and then we multiply by cutoff functions in such a way that we make sure that things glue together nicely. And yes, to prove then that this is a recovery sequence, one has to use the fact that both phi and psi are smooth functions. So we have to Taylor expand. We have to use this crucial hypothesis once again. And then we have to use this following lemma, which allows for easy computations. So this lemma basically tells that for the sake of computing the gamma limit, is enough to look at interactions which are very close, but not too close. They have to be at least larger. Their square has to be at least larger than 1 minus s. And then how does one compute then the limb soup of this quantity? You split it as integration of different possible types of interactions. So you have interactions where one point is inside the inner triangle and one point is outside. You have integrations where one point is in between the intermediate triangle and this other purple triangle, and then you have points which are interacting between two different triangles. In this case, the integration, the computation tells us that this limit goes to 0. In this other case, basically the reasoning that we have done for affine functions tells us we will recover this from through this procedure. And then one will have to sum up what you obtain on each simplex to obtain this final inequality. This is more or less the gamma limb soup. As for the gamma limb info, the situation is a bit more complex because it's rather more technical. So I'll give say a hint of how it's proved. So what we'll prove is that for any omega prime compactly containing omega, and for any u in L2, and for any sequence u epsilon converges strongly to u in L2, this inequality holds true with omega prime here instead of omega. And then by passing to the supremum with respect to omega prime, or using monotonicity from below, we recover the full inequality. Also, one thing that should be mentioned is that, I forgot to mention it before, is that basically, well, in any case, since AOM is an elliptic matrix, this will tell us that if a sequence U epsilon is such that this is bounded, this limit is bounded, that U automatically has to be in W12, which, going back together, makes me think that our result, by choosing A exactly equal to 1, we recover the classical result by Bourgain, Brezis and Mironescu with a different proof, let's say. So for us now, R is going to be a parameter depending on epsilon. The dependence is given by this expression. And so we will start by computing something, by giving some computation with this term with an R here. So what are the main ideas behind our proof of this gamma limit inequality? The first idea was, first one, we have already a gamma limit inequality for homogenization, which is given by the classical homogenization theorem. So we would like to take advantage of this and bound our functional f epsilon s from below with integrals where the difference quotient is replaced by the modulus of the square of the modulus of the gradient of some auxiliary functions. And hopefully we will be able to do it in such a way that this v epsilon, the auxiliary function, is still convergent to unit 2. If we are able to do this, then by applying the classical gamma limit inequality, we should recover our gamma limit inequality for this f epsilon s function. And the second hint is that we have one way to transform gradients into difference quotients when our function u is not any function, but is, for instance, given by affine interpolation of linear functionals which are defined on the coordinate axis. I mean, if you have a sort of affine functions, then this norm of the gradient is going to be equal to this difference quotient. So this gives us a hint on how to choose these functions v epsilon, and we should choose them in such a way that at least locally they are piecewise affine, so that we can use this beautiful inequality to transform difference quotients into gradients. Okay. Before constructing this the epsilon, we have to do a bit of a technical detour. Okay, for us, V is going to be an orthonormal basis, the space of orthonormal basis, and Vn nu is going to be the subspace of orthonormal basis whose n entry is fixed, whose nth vector is fixed and is given by nu. Okay, so by plugging it back together u epsilon inside of f epsilon s, we recover this with the R that we mentioned before. And by a change of variable and let's say Fubini, we can split this integral in this way. And now we have taken outside the eta to the power that we don't like outside, so that here we have just a square. Good. Then we can, again, using the Goria formula, split this as an integration first on radian and then on the sphere. And then we may notice one thing, that we can see this function here as a function defined on the space of all our orthonormal bases whose entry is ni, by simply setting it as a constant on that space. So we can integrate for free on the space of orthonormal basis by using the right measure, which is in this case is the Hausdorff measure on the space of the kd minus d minus 1 dimensional of our Hausdorff measure, where kd is the Hausdorff dimension of the space of all orthonormal bases in Rd. But I mean, we have to do it by paying the price of multiplying by this renormalization factor. And since we want to do this operation for any n between 1 and the dimension of the space by multiplying by 1 over d. And then by observing that basically how can the space of orthonormal basis be parameterized by first you give me a vector in SD minus 1, and then you specify which are the other vectors that form the orthonormal basis. By this sort of identification, and using more formally this formula, which looks very complicated, we recover this inequality where now instead of having V nu n, we have the full space of orthonormal basis. And here we have an integration with respect to the HKD Hausdorff measure. So once we arrive to this point, we are ready to introduce our auxiliary functions. Okay, instead of doing this, let's show first a picture. We want to decompose, the idea is that we want to decompose omega, our domain, let's say as the union of cubes and cubes that are well contained inside of omega. And on each cube, we want them to split into triangles And on each triangle, we are going to define as a fine interpolation our auxiliary functions. So we need a way to decompose general cubes into simplices. This decomposition is given by Kuhn's decomposition, which, I mean, here's, let's say, a proof of Kuhn decomposition in d equal to 3, proof by picture. But it can be done in any dimension. And yes, I mean, here, these are the names of some etiquettes. Let's say the number of simplices in Kuhn's decomposition is equal to the number of permutation of numbers within 1 and d, because they are indexed by permutations. So it's the number of simplices appearing in the decomposition is d factorial. There is a reason why we chose specifically Kuhn's decomposition, but it's just a technical reason. Then we introduced one of the last notational nightmare, and for us, I rho rho bar is going to be the sets of indices in a grid of, let's say. So pick the grid within the integral coefficients that is determined by the orthonormal basis nu bar, and then shrink it by rho and by r. I rho r nu bar is going to be the set of integral indices, such that if you attach to the pointer k a cube with side length r times rho, this is well contained inside of omega. Just another technical thing. Okay, now we are ready to define our auxiliary function. This nu, and for any given positive number, for us, u rho nu bar epsilon on the points of this lattice that we have defined is going to be given as an average of u epsilon on the cube given by the orthonormal basis nu bar and by r rho as a side. Then on each every simplex of this decomposition, our functions are going to be given as the fine interpolation of the values that we have assigned at the vertices of the simplex. And what I mean, if one looks at the construction, it's then clear that the functions are continuous. They are bounded. In addition, they are in W12 of the union of all the cubes, which are well contained in omega. Then, I mean, if you wants to define it on the whole omega, you can set it to be 0 outside of the union of these cubes, but we are just going to consider it on the union of the cubes. Why are they useful? Because, well, using that equality that I wrote before that transforms gradient into different quotients, then one with some computations, so using Jensen inequality and stuff, is able to prove this inequality that relates different quotients with the gradients. Here we are integrating on a simplex, here integrating on a cube, then summing up together things, everything cancels up nicely. Then plugging this inequality back to using it together with the change of coordinates that we've done before, what we recover is this inequality right here. I mean, one has to be a bit careful, because this inequality, we prove it without the coefficient a here in front. But then a was chosen to be uniformly continuous, because you can take it outside, inside, without too many difficulties. So we also recover this inequality with the coefficient a inside. So in the end, we arrive at noting that letting r go to 0. By choosing r small enough, any omega prime compactly containing omega is going to be contained in the union of these cubes, which are going to converge in measure to the full omega. So we recover this inequality right here, but now we are happy, but not that happy, because here we have the gradient of a function, but this function still depends on me and on rho, and this we don't like it that much. So to take care of this, we need to average. So what we do, for any epsilon, we introduce this measure. The dependence on epsilon is given by the fact that we have here an s, which is a function of epsilon. This turns out to be probability measure, thanks to thanks to the fact that we have the right functions and the right constant in front. And so the inequality that we had before the last term of the inequality, this here, might be rewritten using these measures in this way. Now we may use Fubini and exchange the sign of integration, use Jensen from the other side if you want. And now here we have something that we like more. Because now we have this integral performed on the space of the product space 0, 1 times V, which is exactly what we wanted, because now if we define U epsilon bar, the final auxiliary function, as the average of this U rho nu bar epsilon with respect to the measure mu epsilon, then it turns out basically by the dominated convergence theorem that these are continuous, that they belong to W12, and in addition that if you take the gradient of this function, this is exactly basically what we had inside here. So, I mean, we would be done if we were to prove that U epsilon converges to U strongly in L2, which it is true. It is very technical, so I'm going to avoid it. But basically, this allows us to conclude because I mean, here we have a number which converges to 1, and then by using the classical gamma limit inequality for the homogenization theorem and this fact, one is able to conclude what we wanted. And yes, this concludes basically an overview of the proof of the result that we have proven. Then, yeah, that's it.
So first of all, super thank you for your talk. And I don't know if there are any questions from the audience.
I have one. Have you tried like a new trick when you have the integral and you have the kernel which is singular?
Mm-hmm.
Have you tried to switch to time the problem in space? Like you write the kernel as the integral of the Gaussian solution of the heat equation. Weighted.
No, we didn't try.
Okay. No, I mean just if you know if you can avoid the decomposition of maybe it doesn't work and it's just
no, we didn't try it. I never thought about it. To be fair, we always stick to with this discretization procedure. Yeah, I think we changed a couple of times the idea on how to do it, but the idea was always to discretize and to do it. Let's say getting our hands dirty.
Okay. It's just because then maybe you can try like with T you change variables in T and you put the S. I don't know how to explain it, but no, whatever, it's fine.
I mean, we can talk about it later,
Okay.
more specifically. But no, we just tried this way and it worked. And then there are slight variations of this problem that we try to tackle because we try to study the case 1 minus S much smaller than epsilon squared.
Yes.
I mean, one could ask, could you study the opposite problem? No, yeah. 1 minus S much larger than epsilon squared. And that one we didn't. I mean, we tried to do it, we couldn't, but we didn't try in that case exactly this discretization procedure. Many ideas were thrown out. This didn't quite work. Maybe, you know,
when they have comparable scale, what happens? Sorry,
we don't know exactly.
Okay.
I mean, there was a conjecture, but it might be that there is not one critical scale. I mean, there is a range of.
Any other questions or whatever? Oh yeah, also if there are questions online, I don't know, maybe you better see the computer. Yeah, maybe just deactivate the
What should I do?
No, on your top.
The volume or the microphone?
Volume is okay. Otherwise, I think we can send once again Davide.